speaker is Guanan. He's a student of Lina, actually, and then he did a postdoc here with Stephen and Adam. So you're really the member of the NET lab. Okay, so he will talk about his recent work on reinforcement learning.
Okay, thank you for the introduction. My name is Guanan, and as some of you may know, I did a postdoc at Caltech with Stephen and Adam from 2019 to 2021. And I was thinking, what is the earliest memory that Stephen might have on me? And I was thinking about that. I feel Stephen must remember we were both in the Simon's workshop for like one semester in 2018. Yeah, and today, to start, I'm actually going to share a even earlier situation. I'm sure Stephen doesn't remember, but it has actually a very big impact on me. So it was 10 years ago. The background is that I was an undergrad student, senior, trying to apply for grad schools. And then for those of you who know me, currently I do a lot of theory, but back then I was trained in a mainly engineering fashion. I did most of my undergrad training in pure engineering without much fundamental research or fundamental understanding of these engineering problems. So I was very sort of unhappy during that time, for two reasons. One was, firstly, I need to get myself into a grad school, which was tough. And secondly, this type of engineering sort of education, without too much fundamental mathematical aspects, wasn't really too satisfactory to me. So I was really trying to also search around what is the right research for me. And then I came across this Stephen's paper, I believe it's Javad, on the zero duality gap on OPF, which really blew my mind because I didn't know that there could be such beautiful mathematical way to study this kind of engineering systems. I was really impressed. And then I think, I must get into Stephen's group. And then I sent an email to Stephen, and then saying I'm really, interested in this type of research. I mean, today as a faculty member, I receive similar emails, and I don't respond to most of them. but Stephen was really nice. He actually responded to me. And let me show you the response, which I found out just dig out yesterday. So you can see the time. It was 2014, February 10th. And then, the first sentence is like, thank you very much for your interest, and then blah, blah, blah. And then I was basically saying I wanted to do the OPF stuff, and then Stephen said, what you said about the OPF paper is very good. I attached a draft of the tutorial. And then in the attachment, it was actually this paper, which I believe at that time wasn't public yet. It was the tutorial paper on the OPF. It was in the TCNS, the journal. And then this paper, because this paper was written in a tutorial manner, which really I was very impressed. And then I read it very carefully. And also, I was very interested in this research. And also, partially, I was trying to maybe impress Stephen. I was trying to do some proof. Because I think the proof was in part 2 of the paper, right?
The published version didn't have proof.
Anyways, there was no proof. And then so I was thinking, maybe I can just do the proof and then maybe impress Stephen, blah. So I did. So yes, I did actually try to prove the theorem and then send it to Stephen. And then Stephen actually also go back to me, and then we had a few email exchanges. I think the first one saying, your reasoning is exactly right, and then the second one is saying similar things. So so I think I mentioned this because this I would say this very brief interchange, which I'm sure Stephen might not remember, actually had a very profound impact on my research interest, because previously I didn't know that for this kind of engineering there was a more mathematical way into studying that. And then after reading these papers, I directly realized that this type of research was the research I really wanted to pursue, and that started. Even though I didn't end up getting into NET lab, but this sort of shaped my research interest for the decade to come. So you can see this was a little bit more than 10 years ago. So thank you, Stephen.
One of my worst mistakes.
Maybe Lina can comment on that. Okay, so, okay, thank you, Stephen, and happy birthday. And then in today's talk, I'm just going to briefly mention some of the research that I've been doing. As you all know, we are in the age of AI, and then there's a lot of models being developed in the past decade, including deep RL, including these large language models, and also including these image and video generation models. And in this age of AI, so similar to many of you, I sort of have the background in this kind of traditional network control systems, including power grid, multi-robot systems, and then, or maybe general network control systems. So given the AI age, every day I wonder, with the advancement of AI, what is AI's sort of relevance to this kind of traditional control systems? So one way to think about that is, what if you just apply AI-based methods like deep RL to this kind of underlying system? So what is the potential advantages in doing so? And my understanding is that one advantage of AI and deep RL is it doesn't need to know a model, which can be helpful in situations where the model is either fully or partially unavailable. For example, it could be some parameters in the model is unknown, or it could be there are some parts of the system that's very hard to model, like human behaviors, or it could be some disturbances that AI can help to predict. So this is the first advantage. And then the second advantage, I would say, is a lot of times, even if you know the model exactly, the control problem is hard. It can be non-convex, like in distributed control, distributed nonlinear control. These problems are all like non-convex, and then it's hard to find the controller anyway. So in these scenarios, deep reinforcement learning can potentially help. It might not find the exact optimal solution, but due to the expressive power of deep neural networks, it can help at least try to improve the control performance for this kind of non-convex problems. And then there's also advantages in online adaptivity. And indeed, given these advantages, there has already been some small success stories, like people have used deep RL to train this drone racing and have beaten the best human performer in the drone racing. This is in Switzerland, I believe. And there's also other similar success stories. But despite these success stories, there's also many challenges. So all AI models, including deep RL, requires really a lot of samples and computation power to really train. And then this is the number of samples it takes to train the first deep RL model. And given this very large sample complexity and also very large computing need, you might wonder this might not be scalable for large-scale systems. And indeed, if people try to do multi-agent reinforcement learning, it is very hard to scale up. And this is one of the prime examples of multi-agent RL. You can see that it's mainly for relatively small systems, like tens agents, maybe 100 the most. And if you think about large network systems, we are definitely having much, much more agents than this. So scalability is a big issue. And we also have the issue like safety, which Nico also commented on in the talk earlier. So this will make me wonder, is AI really relevant in this kind of large-scale systems? So to answer this question, I take a step back. So this is the picture I showed you when I say apply AI to this underlying system. But the reality is more like this, because the AI model doesn't really care what the system is. It just sort of blindfoldedly apply methods to this kind of system without actually thinking about what it is and treating it as a black box. And as Shrikant and also I guess Minhua mentioned, as control engineers, we know a lot of structures. Even there's no structure, we impose structural assumptions. So indeed, there's a lot of structures underlying the system. So for example, the structure could be the network structure, the network topology, which could include things like the topology in the energy network or the topology in the transportation network. And there are also similar structures. So this is what I call locality-based dynamic network, you can think about in a multi-robot system. Each robot is having interactions with nearby robots, so the robots within a distance. And then since the robots are keep moving, so you can think the neighborhood is keep changing. So this is like a time-varying dynamic network. And example of this will be if you want to do collision avoidance, then you want to avoid colliding into your neighbors, and your neighbors are keep changing over time. So this is kind of a sort of a time-varying network. So these first two examples are all like locality and network-based examples. And there's also examples that are beyond just the network. For example, in many situations, like in power system, when you have to do the demand response, there's a load aggregator trying to aggregate a bunch of loads to satisfy some demand response target. This, you can see there's kind of like a homogeneous structure in the clients you are dealing with. You are dealing with a large population of very diverse, but also sort of similarly structured clients. And lastly, a lot of times we just have a physics-based model that you can write equations down for. For example, while the power system dynamics is quite complicated, you can just write down this simple second-order dynamics equation for this system. So my research is basically asking myself, as control engineers, we know a lot of the structures, a lot of types of structures in this underlying system. But in the meanwhile, many of the AI, like reinforcement learning methods, do not use the structure. So how do we exploit the structure that can help to improve the scalability and safety of multi-agent RL? So this is the general question that I've been asking myself for a long time. And I've also been doing a lot on this. So for those of you who already know me, I already did a lot of work when I was here at Caltech on how to utilize the network topology, improving the scalability of multi-agent RL. And me, Steven, Adam, and Lina had a bunch of, and also Ihan, I guess, yeah, had a bunch of papers on this. And today I'm not going to talk about this. And today maybe I will just show an application of this, this framework, and then in a inverter control example. So this is a paper that we did last year, and then the first author of this paper is actually, we will be the latest member of NetLab joining this next semester. And then we apply this, our concept of structure exploiting MARL to this microgrid voltage control problem, where we actually built a relatively detailed inverter-based distributed generation. We actually had a 13-state model for each of the inverter, quite detailed. And then the goal is to sort of do voltage control. And just as Steven mentioned, we are transitioning towards a lot of the inverter-based resources. And in my opinion, doing, when you have a lot of inverters, doing the control like of frequency and voltage will become much different than how it is done today. So I feel this is the place where maybe RL can potentially help to coming up with a better controller than the state of art. So this is the setting, and then we sort of try our methods on different systems, and then so the takeaway is that if you do this on small systems, our approach, which exploits the structure, is kind of similar to the black box benchmark. And then I actually had two benchmarks. So if the system is small, we don't have, it's sort of similar. But when the system is becoming like larger and larger, so this is like this is a figure with 84 inverters, which is like 84 agents. We can already show our approach is achieving the best among the, when compared to benchmarks without utilizing the structure. So this is basically trying to say that indeed by exploiting the network structure, we can make reinforcement learning more scalable when we scale the network size up. So this is some results. And then you might also wonder for this problem, how large we can actually get. We can actually do 120 agents in this system, while for the similar problem, the state of art was like 40 agents. So we can have a great improvement in the scalability by doing the utilizing the structure. And I feel this number 120 is currently limited by the very bad simulator that we wrote for the inverter, which was really bad. So we didn't optimize on that. If we could have had a much better simulator, this can even go higher. And yes, we also have some results showing that currently these existing inverters are mainly using this PI control, and then traditional PI, and this is like the voltage violation in this radial graph. And by using this RL, we can help coming up with a better controller that improves upon the PI controller. So it feels that I'm out of time, maybe, I don't know. Yeah, so, okay, so I also want to mention briefly some of the other results that I've done recently. So going beyond this static network setting, we're moving to this like dynamic network setting where the network is keep changing based on the locations. So the situation will become much more complicated. And then me and my first student at CMU, we studied this problem, and then we actually had some very interesting results on how to exploit structure in this setting. And this will appear in ICML in 2024 this year. So I'm very happy about these results. We also have some results on utilizing these homogeneous structures, and we utilize this so-called power of k choices type of trick in this multi-agent reinforcement learning setting, and we also have some results. And finally, I've also been working on how to utilize the physics structure in the context of control problems, and this is done in collaboration with my colleague in robotics, Guan Ya, who is also a CMU a Caltech alumni. And we have worked on how to utilize the physics model to improve the sampling-based MPC. And very recently, actually 3 days ago, we also had a paper submitted to NeurIPS, which looks at how to use doing diffusion for trajectory optimization. So diffusion is like a generative AI model, and then it recently has gained popularity using diffusion models to generate trajectories for very non-convex control problems. But most of the existing work are using the model-free way of doing the diffusion and does not utilize the model information. So we propose what we call a model-based diffusion, which uses the physics-based model to help calculate the score function in the reverse diffusion, and we show our results have better performance, less samples, and better constraint satisfaction. So, I mean, this is just like a high-level overview of my research. I'm really a fan of utilizing structures in these kind of AI and RL settings, and I have done this type of structures. I'm very excited to explore a lot of problem-specific structures and use them to make AI and reinforcement learning really relevant in these kind of network control settings. Thank you.
Thank you. Any questions?
So in the comparison you showed, you compared it to the black box RL, right?
Yes.
Can you do anything model-based to compare to?
So again?
Since you have these detailed models, can you do any model-based control other than PI?
That's a good question. So I think this is like a nonlinear and distributed control. I actually do not know what is the best way for model-based control. Do you know? I don't know. Yeah, I mean, PI is what's used in
I didn't see the model, but
yeah, I think it's nonlinear and also, yeah.
What's the network, actual number of nodes in the network? Is it like each DG is one node, or is it
that's
each
a good
DG
question.
corresponding
So
to many nodes?
I didn't show that exactly here. Let me see if I have a picture. Yeah, for example, in some simulations, we just take the IEEE system and then we use a subset of the nodes and place an inverter resource there. So we sort of do that. I think for the IEEE bus, there are already like some generators. We just swap that with inverter-based control, and then we also add a bunch of other inverter-based control at other nodes. So it's like, for example, this is like 145 bus and then 114 DGs. And then, so when I say that this, scalability, I really mean the number of inverters. The number of bus is actually can be larger.
But then in your neural network, what's that structure? Is it like one node to one DG or one multiple?
That's a good question. So I guess I didn't show the details. So I guess we are using a actor-critic structure for reinforcement learning. So there will be like basically it's like one neural network for each node, but this neural network is relatively not taking the entire network.
I see. So you basically have 120 neural network.
But relatively small ones, not a.
Yeah, the smaller one.
Yes, yes.
And then the structure is on top of that.
Yes, yes, sort of. Yes.
Actually, for each of the network, how large is it?
You mean the neural network?
Yeah.
We use the simplest one, I guess, only like MLP, multi-layer perceptions, I think 3 to 4 layers, and then maybe 100 something neurons each. It's simple ones, yes.
Okay, great. Let's thank our